Today I will be talking to you about performance contracts for software network functions. This is joint work with my colleagues at EPFL and my advisors Katerina Argyraki and George Candea. So I'm going to start with a quick one-slide introduction to software network functions. So software network functions, or software middleboxes, provide the increased flexibility of the software development cycle and potential reductions in capital and operating expenses. On the downside, however, concerns remain stemming from the fact that 1, frequent reprogramming is likely to introduce bugs, and 2, replacing specialized hardware with software running on general-purpose commodity hardware can introduce unexpected performance behavior. And in this work, we're going to focus solely on this fourth and final bullet. So the goal of this work is to provide NF developers and network operators with comprehensive understanding of the entire performance profile of the NF before it is deployed. And armed with this understanding, operators can now conduct precise capacity planning and mitigate attacks, and developers can take more informed development decisions. Now, there exists prior work that has taken great strides in trying to achieve this goal, but they fall short on 2 counts. First, they typically focus on a narrow subset of workloads that the NF can face, focusing either on typical common case workloads or on purely adversarial workloads. Second, they are best effort approaches, and so they offer few, if any, guarantees regarding the completeness of the scenarios that they cover. Now, in this work, we're going to build upon all of the prior work, but we do something different. So in our work, we propose the construct of performance contracts for NFs. Contracts provides users with an abstraction that allows them to easily parameterize arbitrary input workloads, whether typical, exceptional, or adversarial. Given only this abstract description of the workload and not a concrete instance, the contract will predict the performance of the NF without actually running it. The performance predictions are in the form of human-readable formulae, which we express as a function of workload and environment variables that we together call performance-critical variables, or PCVs. And finally, although the notion of a contract is independent of any performance metric, in this work we focus on 3 per-packet metrics: the instruction count, the number of memory accesses, and the latency, which is the number of execution cycles. So the rest of my talk is structured along the following lines. I will first illustrate to you what I mean by a contract. Then I will describe how our prototype Bolt generates contracts from NF code, and then finally present a few results from our evaluation and a use case where Bolt can be of utility to network operators. So to illustrate the notion of a contract, I will be using a simple Mac learning bridge as a running example. So let me quickly walk you through it. The bridge receives the packet, and it first checks if the headers are valid or invalid. If they're invalid, it drops the packet immediately. Next, it learns the source MAC address, associating it with the port that the packet came in on. Then it checks if the destination MAC address has already been learned, and forwards or broadcasts the packet accordingly. And in this example, the MAC table is implemented using our standard CS101 hash table, with each hash value having an associated linked list. And in this implementation, the performance of your standard put, get, and delete operations are simply a linear function of the number of collisions that the key encounters. So with this NF and implementation in mind, let's take a look at a contract. So the contract is going to be represented in the form of a table with 2 columns. On the left, you have each traffic class that the NF treats differently. Together, these traffic classes are going to cover the entire input space of the NF. And on the right, you're going to have the predicted performance, which in this example is for the metric, the number of lines of pseudocode. So in this NF, we have 3 packet classes: packets with invalid headers, packets with valid headers whose destination MAC address is known, and packets with valid headers whose destination MAC address is unknown. And finally, the performance. For invalid headers, you have a constant cost of 3 instructions, while for valid headers, the performance is a linear function of the number of collisions you encounter during your put and get operations. And here, the performance is represented as a function of C, which is the number of hash collisions, which is the performance critical variable for this NF for this metric. So let's assume a tool generates this contract for you. But how is one supposed to use it? And the idea here is that the user can query the contract with constraints that specify the properties of input workloads of interest. So let's start by looking at the broadest possible packet class, unconstrained traffic. Now, by definition, this traffic class does not preclude any of the sub-branches in the contract, and so multiple performance predictions are possible. In this scenario, the contract, being conservative by design, will return the performance of the worst case traffic, which here is the broadcast traffic. Additionally, since the user has not specified the number of hash collisions, the contract is once again going to assume the worst, which is that the maximum number of collisions occur, and so the predicted performance is as shown. Now, this is the absolute worst case performance of the NF, but this number alone is not of much use to an operator, because this scenario is very unlikely. And so to this effect, the user can progressively add more and more constraints to the workload specification to scrutinize performance at finer granularities. So let's say the operator wants to understand the performance for more realistic traffic where hash collisions are rare. Once again, all three traffic classes are feasible, so the performance returned is that of broadcast traffic, but this time with only the constant 100. And finally, if the user specifically constrains the input workload to valid traffic whose destination MAC address is known and suffers no collisions, the contract is going to return the value 20. Now, in this toy example, we had only 3 traffic classes. But for any realistic NF, you're going to have between several hundred to a few thousand traffic classes. And there you can really appreciate the value of being able to progressively add constraints to the workload specification to understand performance at finer and finer granularities. So to summarize, performance contracts quantify the performance of all traffic classes that the NF treats differently. Together, these traffic classes cover the entire input space of the NF. And users can query the contract for performance of workloads of interest. So now that we've seen what a contract is, what it looks like, and how one can use it, let's take a look at how we're actually going to generate them. And the process of generating performance contracts is a recursive one. The highest level of recursion is an NF chain. So given a sequence of NFs connected in a certain topology like this, we want to be able to generate a contract for it. But you can really think of this NF chain as one large composite NF with the individual NFs as building blocks. And so naturally, to build the contract for the chain, we're going to utilize the performance contracts for the individual NFs. So let's zoom in further to an individual NF. When we zoom in, we see that an individual NF can further be divided into 2 parts. You have data structures, which encapsulate the state that the NF maintains, and stateless code that operates on these data structures. So for the bridge I showed you earlier, the MAC table encapsulates the state that it maintains, and the pseudocode interacts with this MAC table using well-defined API calls like puts and gets. And the reason I have modularized the NF this way is because prior work has shown that when you're trying to analyze NF code using automated PL techniques, the part that is hard to analyze are these stateful data structures. So to overcome this, we're going to do the following. We're going to have a very well-defined separation between the stateful and the stateless NF code. This works particularly well for NFs because they typically have well-defined state that can be easily isolated. We're then going to encapsulate the state that most NFs maintain using a library of data structures. And these data structures are going to form the base case of our recursive process. And the idea here is that because we use this library, we can analyze them once using possibly human-aided techniques, and then simply reuse this analysis across multiple NFs that use this library. So how do we analyze these stateful data structures? Now, you can think of the performance of the NF as being a function of the input packet, the NF state left behind by packets that came before, and other factors such as configuration and environment variables. And the reason this NF state or these stateful data structures are so hard to analyze is that it's infeasible to explicitly list every possible sequence of packets that came before. There are simply too many of them. But as you've probably guessed by now, irrespective of the exact packets that came before, the performance of the bridge depends only on the number of collisions they cause in the MAC table. And so, to analyze these stateful data structures, we introduced this PCV abstraction, which abstracts away specificities in the NF state and distills only the key parameters that performance depends on. And so while we cannot explicitly list every single possible packet history, we can capture their impact on performance by using the right PCVs. That said, here are the contracts for the MAC table put and get. The contract for the put is unconditional, but the contract for the get has 2 sub-branches because the code behaves differently depending on whether the key is present or absent in the map. And here C, the number of hash collisions, is the only PCV that we require to summarize the performance of the MAC table for the metric number of lines of pseudocode. Another feature of this PCV abstraction, which I will only touch upon very briefly here, is that it allows contracts to expose different amounts of detail for different users. So for an operator, we can express performance as the simple function of number of collisions. But for a developer who's more familiar with the nitty-gritties of the code, we can actually express it as a more complicated function of the exact struct being hashed and the hash function, which can allow developers to dig in more deeply. The paper talks about this in more detail. So now I've told you how we've analyzed these stateful data structures. Let's now look at how we're going to use them to build contracts for entire NFs. And here we use a technique called exhaustive symbolic execution, which allows us to list all the execution paths through the stateless code of the NF. While traversing each execution path, we're going to tally the performance cost of the stateless code and simply plug in the contract for the stateful functions, these contracts we've already built earlier. So let me walk you through a quick example. We're now going to build the contract for the Mac learning bridge, the one I showed you earlier. So the first instruction that we hit is an if, which can have two branches, depending on whether headers are valid or invalid. For invalid headers, the cost is 3 instructions, while for valid headers, the cost so far is only a single instruction. Next, we hit the Mac table put. Here we simply plug in the unconditional put contract. Then we hit another if, which can have two branches, depending on whether destination MAC address is known or unknown. And here we use the path constraints to pick an appropriate subclause in the contract. So for the path on the left, because the destination MAC address is known, we pick the top subbranch, and the path on the right, we pick the bottom subbranch. Finally, we explore both these paths to their logical conclusion and add in the costs of the broadcast and the forward instructions. And now that we've explored the entire NF, we can simply create the performance contract. Each traffic class is characterized by the conjunction of constraints that held along the entire execution path, and the performance is simply a sum. And because we've explored the entire program, the traffic classes put together cover the entire input space of the NF. So that was performance contracts for individual NFs. And now we're going to use them to build contracts for NF chains. And here, the process is a very simple one. What we do is we take each pair of communicating NFs, we pair together the packet classes from their respective contracts, and we add a symbolic constraint which equates the packet sent by the first NF to the packet received by the second NF to capture the interdependency between them. So let me walk you through a quick example. Consider a very simple chain. You have a firewall which drops packets with IP options, and a router with a fast path for packets with no IP options, and a slow path for packets with IP options. And in this chain, the router is never going to see packets with IP options, and the composite contract must reflect this. So the first step, naturally, is to generate their individual contracts. Both have two packet classes, F1 and F2 for the firewall, R1 and R2 for the router. And when we put these two contracts together, we'll see that the only packet class pairs that are feasible are F1 alone, because it drops the packet immediately, and F2 with R2 for packets with no IP options. And you'll notice that this captures the interdependency that the router will never see packets with IP options. And this is something you will have not obtained if you simply added the two individual contracts together. So now I've told you how we build performance contracts, starting from stateful data structures to individual NFs and all the way up to NF chains. Let me now walk you through a few results from our evaluation and a use case. So in our evaluation, we test Bolt on 4 NFs, a NAT, a Maglev-like load balancer, a Mac learning bridge, and an LPM router. And here, when we generate the contracts for each of these individual NFs, we analyze not only the core NF logic, but also the DPDK packet processing library and the NIC driver. And our contracts quantify performance in terms of 3 metrics. In the interest of time, I will only be displaying the results for the first 2. You can refer to the paper for more details. Our test bed looks something like this. You have a tester which generates and sends test traffic, and a device under test which runs the NF. And both are Intel Xeon servers with 10 GB Intel NICs. And the methodology we're going to use here is that for each NF, we're going to identify a few packet classes, generate the test traffic, measure the performance on this test bed, and then compare this measured performance to the values predicted in the contract. So here are the results for our Maglev-like load balancer. Here we have 5 packet classes. First, you have unconstrained traffic, then 3 packet classes for packets coming from the client side, belonging to a new flow, an existing flow whose backend is now unresponsive, and existing flows whose backend is still live. And also, we measure and predict the performance for heartbeat packets from backend servers. And for each of these packet classes, we're going to plot the prediction gap, which is the difference between the predicted and the measured values for both instruction count and memory accesses. And I want to point out here that contracts are conservative by design and will never under-approximate performance. So the prediction gap is the sign difference between the predicted value and the measured value. Here are the results for the instruction count. As you can see, irrespective of the packet class, the prediction gap is less than 8%, and the results for the memory accesses are similar. In fact, the maximum prediction gap is 7.5% for the instructions and 7.6% for memory accesses. And the results for the other NFs are similar, and you can find them in the paper. Now, this raises an interesting question as to why there is a prediction gap in the first place. And the primary reason for this gap is due to a design choice we make in the PCVs that we choose to expose. At times, we trade off precision for legibility and coalesce multiple execution paths together, taking the performance of the worst. Naturally, this leads to overestimations. Keep in mind, however, that when we design contracts, we always design them with the target audience being a human. It's not infeasible to envisage a situation where the target audience is a machine, where we can expose additional details and bring down this prediction gap. The second reason stems from the fact that there are slight differences between the production code and the code that we analyze. These differences are necessary to enable exhaustive symbolic execution. And to ensure that we never under-approximate performance in this scenario, we disable certain link time optimizations in the analyzed code, which reduces its performance, and so once again, we have overestimations. Now finally, let me walk you through a use case scenario, which will illustrate how an operator can use performance contracts to perform a more informed cost-benefit analysis. And actually here, cost is performance cost, not monetary cost. So consider a bridge that has a more complex hash table, which is going to defend itself against collision attacks. And this hash table has a random key in the hash function, and whenever the number of collisions crosses a certain configurable threshold, it's going to change the key, rehash all existing keys, and rebalance itself. And the question that the operator faces here is where to place this threshold, because this rebalancing is expensive and must not be done under normal operation, but needs to be done when an attack is suspected. So how does Bolt help operators answer this question? So the first step, naturally, the operator takes the NF and generates the contract. It looks like this. The performance is a function of the PCV, once again, hash collisions. And you can see that there's a very clear cliff, which indicates the rebalancing. Here, the threshold is 6, which is where the cliff is at. Now, to help the operator understand where to place the threshold, Bolt, when given a specific packet trace, plots the values for all the PCVs for each packet in the trace. So here, the operator will notice that for a uniform random test workload, only 0.2% of the packets incur more than 6 collisions. And so if he or she sets the threshold to 6, the operator is confident that for 99.8% of the packets, only around 1,000 instructions will be executed. Now, if the operator wants the rebalancing to be more or less infrequent, they can move the threshold to the left or the right, and the contract will reflect the changes. So the takeaway from this is that Bolt gives the operator better tools to reason about the performance trade-off here and allows them to visualize the consequences of their decisions. So to summarize, today I have told you about performance contracts for NFs. Contracts provide users with an abstraction that allows them to parameterize arbitrary input workloads, whether typical, exceptional, or adversarial. Given only this abstract description of a workload and not a concrete instance, the contract will predict the performance of the NF without actually running it. And finally, the performance is predicted as a human-readable formulae, which is a function of what we call performance-critical variables, or PCVs. Please visit our website where you can find the Bolt source code, the NFs we tested it on, our paper, the poster, and additional details. Thank you for your attention, and I'm happy to take questions.
One so from Sonos. So very nice talk. So it reminds me of one of my colleagues actually back in graduate school working on the worst case time execution on the dynamic kind of processor. So how do you consider those dynamic nature of modern processors, like the cache, like a data caches, instruction caches, and then branches? Do you actually always assume that cache is always missed and then branch is always not predicted well?
That's a great question. So the idea here is we're going for example, for latency, right? We need to model the behavior of the processor. And here what we do is we build a model, but we ensure that we're always over approximate. So we assume the cache, we miss in the cache, unless we can definitively prove by tracking the spatial and temporal locality that the cache block is indeed in the L1 or L2 cache. And so what we do is we model the cache hierarchy, but for instance, because we're conservative, we sometimes have to take in more cold misses that will actually occur. Because, for instance, we do not know what packets that came before left behind. But we do our best to track most of this. But when we can't, we remain conservative and slightly over approximate performance.
Okay, good. One follow-up question is, how did you find that average execution time versus the worst case execution time? Like, is it order of magnitude of 1 or 2?
So that's a good question, right? But here the question is how you define average. Now, if you're defining average over a probability, that's hard because Bolt is a static analysis tool and has no idea of what kind of traffic you're going to face, right? But if you just pick an average as all the execution path and pick a median, in general, it depends on how well or how badly your NF is written. But typically, because of the dynamic nature of the state, the average is much better than the worst. For example, in the example I showed you, the worst is when you have all the collisions, which is infeasible. But because a static analysis tool will take that into account, that path exists. And so the worst is typically orders of magnitude worse than an average or typical case workload. In fact, in our evaluation, you'll see that the actual worst case is 9 orders of magnitude worse than the average case.
I see. Thank you very much.
Sujin from CMU. So is the traffic class part of the input to the tool, or how do you know that in advance?
No. So the traffic class depends on the NF. So the tool is going to analyze the NF code, figure out which traffic classes it treats differently, and simply going to create individual execution paths for each one of them. So for the bridge, you'll have broadcast traffic and unicast traffic. For load balancers, you'll have new flows, existing flows. But this is, again, completely dependent on the NF. And so the tool will take the NF code and generate all of these paths. And the user then just specifies which path he or she is interested in.
I see. So if the source code has many numbers of code, if you have too much traffic class, then the performance contract might not be as useful as you hope that to be, right?
Yes. So like I said, in a realistic NF, you will have between several hundred to a few thousand execution paths, which is where you can then provide constraints at arbitrary levels of arbitrary granularities to understand workloads of interest. So for example, you might say new flow, which will have, let's say, 1,000 execution paths. Then you might say new flow, which has this other condition, which will be 500, and so on and so forth. And you can dig deeper based on your needs.
And when you say real NF, do you mean open source NF, commercial NF, or click-based NF? What do you mean by real NF?
So the NFs we tested on, we wrote ourselves. And the primary reason for that is because of the stateful, stateless separation that we employ. So we did consider taking an open source NF and porting it, but we realized that by the time we were going to be done with it and enforce the stateful, stateless separation, it is going to look like we wrote it from scratch. So we didn't do that.
Okay, thank you.
Yeah.
Hey, Rahul from CMU. So many of the times the adversarial workloads are designed in such a way to trigger those corner cases. So like if somebody is causing like TCP SYN flood attacks, they would randomize the source IP address so that you can't rely on those link optimizations like caching and so on. So is there a way this framework can be extended to model those adversarial workloads?
Definitely. Because so that's the whole point, right? Because we use exhaustive symbolic execution. If a path exists where an adversarial attack can happen, it will be caught by definition.
But it's more on the static level or the source level. But most of the time, let's say I'm causing a TCP SYN flood attack. I'm trying to get rid of the caching by doing this. So it's more looking at a dynamics execution or how it behaves in practice.
Yes.
It's trying to trigger those corner cases.
Yes. So once again, I'm going to give a similar answer so for the cache model also, because we're conservative by design, in such an example, if a cache flood attack can force an eviction, then we will not be able to prove that the cache block exists. And so once again, we will assume a miss. So in fact, what we did, so we had a paper cache done at SIGCOMM, which does exactly this, right? It generates adversarial workloads. And we compared the latency for a cache generated workload with the bound. And there, the prediction gap, so let's say cache the number measured with cache is 1x. The predicted number is 1.4x. And this 4x is because we're forced to assume one additional memory miss than actually occurs in practice, because we can't prove that the cache block exists in the cache.
Thank you.
Okay, let's thank our speaker one more time, and then. Sorry.